and share the Jupyter Notebook. So we're going to continue with the previous lecture on the topics of using cross-entropy and sigmoid functions to complete a classifier for MNIST classification, basically. So we had gone over this code, and we've defined a few functions, and now we're in the main loop where we need to define the train and the test. So we can do this in multiple ways, obviously, but at the end of the day, you know, we could write all the code in here, or we can break it up in a more modular approach. Okay, so let's continue here. Recording. All right, so we're gonna do 20 epochs, and let's just think that we want to have an epoch for training. So let's call it train epoch, and that's a function we're going to need to define. We need to think about some of the parameters. So we might need the linear function itself. We might need the learning rates, and we might need the params, right? So the params that we define. Once we have that, we want to print how it does, right? So by creating maybe a validation, so we're going to validate epoch, right? So we validate the data. This will deal with the validation data, so the test set. And the thing that we need to provide to this, of course, is the train model. So the train model should be linear, because that brings together everything. So validate linear, the linear function, this one, right? So we're going to make predictions on the test set. So if that's the approach that we're taking, then we need to this one, define those two functions. Okay, so we need to define those two functions. So let's define first train epoch. So I'm going to define train epoch. I'm going to define train epoch. And this, if you remember, takes the model, the learning rate, and the params. So in this train epoch, then, I'm going to train on the train set. So I'm going to do for xb, yb, that's the x and the y's in the train set. So in DL, remember the DL is this object here, which defines the data set for training. It's in batches of 256, right? So we're going to read in those in batches of 256. And we need to do some calculations here. So we need to predict, we need to calculate the loss function, we need to take the backward propagation step. So we can call that function, let's say calcgrad, okay? Calcgrad will take xb, comma, yb, comma, and the model itself, okay? And then once that happens, we will need to update the parameters, right? So we can manually do this by for P in param. So that's the weights and the biases, right? We can get those out. And then we can just update them as we had explained before, right? So if you remember, we had at some point before in one of the previous lectures last week, we had talked about updating weights here, right? Params data, so we update this, right? And so that's something that we're going to do here as well. So we update it. So how do we update it? We need p.data minus equal, so that's just, you know, the same p data minus. And then we're gonna modify it based on the p dot grad values, p grad times the learning rate. So if you remember, we had done this over here. We had explained how that works before, right? So we the params data and then the grad data, and we update it. Okay, so we update the data there. And remember that PyTorch has this thing where you have to kind of, after you update the weights, the gradients, you have to zero it out. Otherwise, they'll accumulate, and that's just a thing. That's just like a mechanical thing. So here, I'm just going to write the comment again, because this is purely a mechanical thing. Delete the old ones. Okay. So we do this process, but we still need to define then the function calcgrad. So that this function should be done now. But what is calcgrad? So calcgrad is the other steps. And like I said, you can write this in other ways. Just whatever is clearer for you. Calcgrad takes xb, yb in the model, xb, comma, yb model. All right, so it takes those three parameters. So this is where we're gonna predict first of all, right? So we're gonna use the model to predict. So we're gonna have preds, model, and it takes what? XB, correct? So it takes a data, a training data, predicts a value, and then it needs to compare. So loss will be MNIST loss, which uses torch.where, aka CrossEntropy. So MNIST loss then takes preds, and it takes YB, which is the real data. It calculates the loss, and then given those values, it does the calculates the gradients. So this is where we do backward. Okay, backward. So when we take this step, we calculate the gradients, and then that way we get the values here that we're going to do the update. So this does the update, but first we need to do the backward propagation. So the way that it works, if you want to think about it, is that look over here. We have a model, a function, right? So we have a function, whatever it is, right? Now, this is the neural net, currently a simple network. That's forward. Now we know true labels, but then there's gonna be pred labels. So take the input, go through the function, we get pred. Now we need to compare these two, right? That's what happens in the loss function. And then we need to go backwards, given that calculation, to adjust all the weights. And that's why it's called backward. That algorithm, backprop algorithm, is very fundamental to do the update. Okay. So that's what we're doing there. So preds, YB, MNIST loss, and we do the back propagation. Any questions there, guys, so far? Any questions?
I don't have a question, but you spelled MNIST wrong.
Did I? Okay.
Yeah. You flipped the S and the I.
Where?
Like 2 lines above your cursor.
Thank you. All right. So then we have the calc grad is done for the train epoch. So that should be complete. Now, we need to do this part, the validate epoch, right? To validate epoch. So we're going to create that function as well. So this should be validate epoch. So define validate epoch. There. We have a model. Define validate epoch model. What do we need? So this takes the model. So we need to predict, right? So, so let's do a list comprehension here. Think about it a little bit. So for xb comma yb in valid DL. So remember, valid DL is this one here, the data loader of batch 256 for the validation data, not the train data. So we get that data, XB, YB, and now we're going to predict. So we're going to take model XB, right, that predicts a value and we just need to compare to the YB. So we need to pass that YB as a tuple. So the predicted and the real, right? So the predicted and the real, and we're going to pass that to another function called batch accuracy that will give us the actual score. So then basically here, what we can accumulate is the accuracies, a list of accuracies for the batches. And then that way we should be able to know the prediction. So then we're just going to accumulate all of them. So then we're going to do return. So accuracies, right? We're going to have a list of accuracies. So then we can stack them. So torch.stack, because this is a list, but we're going to make it into a torch stack tensor. Called accuracies, and then on that tensor we can call the torch mean. And then once we have the mean, we just get the final value item, and we're going to round it to like 4 digits or so. So then this should be round. Oops. So that should be round. Okay. So that should be but we just have one final function then, which is going to be batch accuracy. Batch accuracy should be the last function. And batch accuracy is basically, now our values have to be evaluated. So we're going to do xb comma yb. Notice that the values are always like not within the 0 to 1 range, except in the mness loss here when we call the sigmoid function. And then here, if we don't do that, the values are actually not in the 0, 1. So we need to do that first. So I'm going to do 1, 2, 3, 4. I'm going to create the predictions. are gonna be XB, yeah, XB are the predictions, but I need to make them in the scale 0 and 1, right, like that. So XB sigmoid. Now I can figure out the correct ones. So we're gonna do the same trick we had done before. So correct equals, we're gonna take the preds, those that are greater than 0.5. See now, you know, if they're closer to 1, by being greater than 0.5, they're basically 1s, else they're 0s. And now we're gonna compare this to YB, which has the true labels. And this should give us then the trues and the false. And then now we can calculate the mean. So it's pretty much what we had done before. Return correct dot float dot, and this should give us the accuracy. And I think we are done. And this is kind of the explanation of this. So let me see if this will run. I think I have everything here. So let's save it and run. Accuracy is missing a colon. And there we go, right? So now this is not the loss. We are actually printing every epoch the accuracy, right? Notice that the accuracy goes up to 94%. Questions? Does this make sense? Guys, does this make sense?
So far, yeah.
Okay, great. So now that was the theory. You will not usually write the code like this, right? That's not your objective. So you would want to generalize things in PyTorch even more. But this is good for the fundamentals, the basics. So now let's take the same code as before. I'm literally just going to copy paste it. But let's call this one a fast AI approach. So what this means is that same code as before, but now more fast AI-ish, right? So we're going to use, for instance, one of the things that we can use that we learned was the learner, right? You remember there was a generic thing called a learner. So we're going to try to use that one. So I'm literally just going to go ahead. Okay, I'm going to copy the code here. And we're just going to modify it a little bit to be more, to use some of the fast AI stuff. So here, we have same thing, train X, train Y. We have a D set there, then valid X, valid Y, valid D set. So that's done. We have the DL data loader, valid data loader. But now we can create a combined thing that has both of them. If you remember when you used the learners, you kind of had something like this where you had both of them in one item. So this is called a DLS in fast AI usually. And now we're going to use data loaders, not loader, so that we can combine, we can include both the train and the validation or test set. So this is then made up of DL and valid DL. You guys see that? So we can add that in. The MNIST loss, that should be the same thing. Prediction, sigmoid, yeah, torch.where. but we want to simplify a few things since we're using, so now we're gonna take this out, although this is how it works behind the scenes, right? There are more efficient ways of doing this. So we're gonna take this out because if we use some of the PyTorch built-in objects, then this is built in. So we can take this out. We're gonna use we're no longer going to write the equation, which is not usually recommended. We're gonna use built-in functions for that. The mness lost, that one should be the same because we need a loss function, so we will leave that there. Okay. The batch accuracy, that's also something that we're going to leave. But the calc grad, this and the train epoch where we do this, right? We don't manually have to do this, right? And so this can actually be abstracted for us. So we're going to take out this as well. And the validate epoch, that's also abstracted by fast AI, so we can take it out. So really all that remains is the batch accuracy. You know, how do we measure the performance accuracy and the mness loss? And later, even those could be replaced with built-in system functions, but right now we're just going to leave them. And you've used learners already, so you probably already know where this is going, right? So we have mness loss taken care of. We have batch accuracy, should be the same. And now we just build our model. So we still need a linear function, obviously. Also, actually, the epochs, the learner can take care of that as well. So we can take that out, right? And so now what we need to define is a linear model, right? So linear model, but instead of writing the equation as we had done before, we're just going to use the built-in neural network function linear. Notice that we're not declaring it because we're in the fast AI environment and we can just reference this. If we were just in PyTorch, we would probably have to bring it from Torch. So here the dimensions are still the same, right? 28 by 28 by 1. Remember, we're predicting just, we have 784 input neurons, we have 1 output neuron, which is a 0 or a 1. So the architecture, now architecture starts to become kind of important. And the architecture of this model is like this. This is the input X, and we only have 1 output, which this output runs through the sigmoid function so that the value is, you know, in the range 0 to 1. And then we have a threshold of 0.5 to indicate. So this is the architecture of our model, okay? Basically, it's nonlinear, but it has no hidden layers. It's not a neural net, it's a neural net, but a very simple one. It's not a multi-layer perceptron, and it's definitely not deep learning yet. But you'll see that very quickly, we're gonna get to that. So I go over here to the code, I define the linear model over there. Okay, and now, all I need to do, instead of doing everything that I had done before, I just used the fast AI built-in learner. Okay, and now I'm going to plug in all the parameters. So DLS is the data, and linear model is my function that I have there. It's a linear function as I just described it. The optimization function is going to be stochastic gradient descent. The loss function is going to be mness lost. There it is. Mness lost. And the metrics are going to be that batch accuracy. Okay. So then we just have to tell it learn.fit. Remember, this is not a pre-trained model. We're going to say that we want 40 epochs and that we want the learning rate to be 0.1. Again, play with this learning rate because it's pretty significant, the difference that you get. And you see, this is how fast AI would do it. Notice the difference, everything that we did over here in like pure native PyTorch versus fast AI abstractions. So now I'm going to save it and run it. There it goes. Okay, and the loss function, the cost function goes down. So that's good, right? You guys see that? Does that make sense, guys? Questions? Now I'm going to introduce a neural network. So I'm going to say simple net, and this is just another architecture. So simple net will be equal to nn.sequential okay, nn.sequential. And then here we're going to specify the first is a linear layer that takes the input. So it's 28 by 28, which is 784. Oops, not X, but asterisk, 28 by 28. But now, instead of 1, I'm just going to plug in here 30. And what that means is that I'm making now a hidden layer in this model of size 30. So if I go to the whiteboard again, now we're dealing with architecture. So the architecture of this model is going to be, so if you see on the whiteboard, this is 784, 1, that's X. But now the output is over here and in between, and this is of size 30. So I've added a hidden layer. So this is the input. This is the input. This is hidden 1. This is the output. This is not deep learning because it needs one more layer to be deep learning, but this is a multi-layer perceptron, right? So it's a neural network for sure. It's currently linear, and I haven't finished it. So currently, basically, I have something like that. Notice that this object already has built in the parameters, basically. So we don't have to define that or update it, it just does it. It's nonlinear, so we need to make it, so sorry, it's linear, so we need to make it nonlinear by just doing nn relu. What that accomplishes is that now all these inputs here, sorry, all these neurons here are going to be run through an activation function called relu, very much like sigmoid. Whereas sigmoid had this shape, relu has this shape, the famous hockey stick. And what that means is for negative values, it is 0. So this is basically -1 to 0, well, minus infinity, I guess, to plus infinity. So basically, if the values are negative, it just cuts them off at 0. If they're positive, they're just linear to whatever the values are. So people, researchers in deep learning have discovered that's a very good activation function for deep learning. So pretty standard. All right, and then now you need the last layer connection, which will be nn.linear 30, 1. Okay, and that's that last layer here. So that's this last layer here from 30 to 1, right? So now they're connected. Notice that in that architecture, we just leave this without the sigmoid. So what that means is that the values here can be from -infinity to plus infinity. I'm used to putting in the sigmoid here. This is what I was talking about. And then I don't have to worry about it. But because the code is written the way it's written, we're going to leave it without the sigmoid there. So I'll show you what I mean in a second. So if we go to code here, because we independently call the sigmoid here in the batch accuracy, and then we also call it in the mness loss here independently, then we don't need to do nn dot sigmoid. Okay, we don't need to do that. But this, if we did this like that, then we would take out this line and we would take out this line, which I kind of like it because it's cleaner that way. But the way we have it, we don't need to. Did that make sense, guys? Is that clear for everyone? You guys still there? All right, and then notice that the dimension goes from 30 to 1, right? Because this is 30, so now it's 30 to 1. Okay, so that's our neural net, a simple one. And of course, you can add more layers if you want to, of course, just by adding more and more. And you can play around with that value. Okay, so now that I have this, let's go ahead and replace in the learner itself, instead of linear model, we're going to use simple nets. Just like that. Save and run.
Capital L in the linear, line 43. I just did the same thing.
All right, thank you. Okay, so save it, run it. There we go. Notice that it optimizes, basically. Okay, and the loss function is pretty low. Not sure if this one was better than the linear. I can't remember, to be honest, but theory. And that's it, right? So that does it. That's the function. If you try different learning rates, like if you do 001, something like that, notice that it did not learn. Do you guys see that? The loss function is not working. So this shows you that the loss function is really important, okay? The learning rate, sorry. So I'm going to save, run it, and you can see here it is learning, and you've got a reduced loss. Okay? Any questions? Let's plot the the learning. So let's do plt dot plot. So we're going to see how it does it. So we can do here. L, these are fast AI functions. Take the learn object dot recorder. It's got a built-in recording system, which is really nice, actually. Instead of what TensorFlow 1 used to do, it was so convoluted. Dot values, right? And then dot item got two there. And then that should be it. So if we run this, it should plot. Yep, there it is. So this plots basically that over the epochs, the 40 epochs, look, it learned really quickly, right? So after like 3, it was already above 90. So this was an easy problem for it to learn. So that pretty much completes what we're doing. This is not homework, but let's call it practice for you guys. So I'm not going to give homework today, but just practice. And basically what I will say is build several NN architectures and train and test. Okay, so just try, what I mean by that is change this, add more layers, more things, etc. And that will, help you to practice. Okay, and finally, to conclude today, we did all of this, right? But the point that Fast AI is trying to make is that they have simplified the code. So they really sold it well, I think. So we started from everything from scratch, very PyTorch focus. Even in PyTorch, you wouldn't do it to that level of detail. And so now let's do everything that we've done. Let's do everything that we've done, but the Fast AI way. So now, let's say, or instead of all the previous code, just do this. Okay, so we need the DLS data, right? So the path, initial path was, what was the initial path? This one, right? From URL mnis sample. We're just gonna use this data. So I'm gonna say DLS image data loaders from folder path. So this is just the mnis data. And then we build learn. But now instead of creating architectures, etc., we're going to use the pre-trained model. So we can skip a lot of things because this is the pre-trained CNN learner. If you remember, this one it takes the DLS. It uses the ResNet model. So ResNet 18, let's try, instead of our own simple NN. We say pre-trained. Actually, we're not going to use pre-trained. We're just going to use the architecture and we're going to train on our own data because we do have a train and a test set. So we can say pre-train equal false. the loss function, notice here what I'm going to do. So the loss function, instead of being mness lost, where mness lost is torch.where, where torch.where is the explanation I gave you guys of, well, it's gone already because it's in the other video, but the cross-entropy function from the previous video, previous lecture. So instead of doing all of that, we just used the built-in fast AI version, which is f dot cross. You see that? Basically all that explanation I gave you. And then now the metrics are going to be just a built-in instead of you building one. So, and we just use accuracy. You see that? So now that I've done this, because we're not using pre-trained, we have to train fully. So I'm going to create, learning rate is important, 0.1. And then I'm going to do fit one cycle instead of fine tune. So I'm going to do learn.fit one cycle and one comma. So it's just basically like one epoch. Look at all the data. LR. Okay. And that should do it. So let's go ahead and save and run. And it didn't work. Oh, no, there it is. As you can see, the accuracy after one cycle on the validation set, it is 0.99. The loss function for the validation goes down to 0.01. So that looks good. This is using the data built in. We do have one DLS, right, that we had created our own here. And I don't know if the format is exactly the same one, but let's try that one. So I'm going to save it, run. Okay. And as you can see, it pretty much gives us the same result. So, but I actually, just to be on the safe side, because it may still hold the previous data, I'll run this one. This should upload the DLS to be the one we've been using. Okay, now, okay. And now it's using for sure our data set, not the built-in one. Ah, there's an error. In out is not defined and cannot be in the data. Yeah, I think it's just I kind of expected this. In out. Here it's not defined and could not be inferred.
Should that be like n out equals 1 or?
Well, it's saying that n out is, if I look at this, n out is saying it is ResNet 18.
Oh, I see. Architecture, then n out.
The architecture. I'm betting it has something to do with the data not being in some correct format. But I didn't test this before, so I would have to think about it. Yeah, go ahead.
I was just thinking it was like in our architecture, when we first started, we went from 784 to 1. I was just wondering if that's what n out means.
Yeah, it could be that. I mean, that's a good possibility. There's some difference in the data set that it's not in the right ResNet 18. So the explanation is probably, well, there's a way to test that, right? Don't you guys think? The way to test that is to use our own simple net. Because if we use simple net, that one should be consistent with our data, correct? And ResNet may need the data to be in a little slightly different formatting. So if I do, nope.
I pulled up the CNN Learner for Fast AI. It's got a bunch of arguments you can give it.
Yeah. Yeah, I think I thought this would fix it, but it's obviously, if basically what this is saying is if we got our data in the right format, we would simplify it. I just didn't test this out. And I can't think of it right now. That's not 18. So if we do this, then it'll work. Because I'm betting the image loader does something to the data that we are not doing to our own DLS. Do you guys see what I'm saying?
Yes.
There's something there in the loss function or in the metrics. But anyway, that should be, so that the solution to this would be to put our own DLS in the format of this. We have to look into the details. But anyway, I think you guys get the idea. And that's basically it. So that's the solution. So do you guys have any thoughts on this? As I said, I'm not going to give you a homework. However, I would recommend playing with these, right? Changing that. And also, if you can, figure out how to make the CNN Learner work, not just with this data, but with our original one. Maybe you guys can troubleshoot it and find the solution. Does that make sense?
Yeah.
Questions?
Can I show you what they have here on this thing?
Give me a sec. Let me stop sharing.
I don't know if it's the solution, but
yeah, share it. Go
ahead. So one possibility. Well, I'm looking here, and there's the N out and CNN Learner, and then I noticed they have put a models dot, then the ResNet. I don't know if that would solve our.
What's the definition of N out? Go to where the definition is. N out
right
is
here.
Right, none. Yeah.
So I don't know, but there's the learner.
Yeah, no, I see that. I think the problem is the way the data is structured. See there in image loaders. That's the one that I would have to, I believe this image loaders puts DLS in a different format than the DLS we have. Well, that's the issue.
Oh, using the number of final activations inferred from DLS.
Is there a way to like print the shape or something of DLS for both and then just compare them that way?
Yeah, that's a good.
I wonder if we can just pass the one value to it. Right there, it says otherwise pass the value to N out.
Yeah, you're saying like N out equal 1.
That's just a guess, but yeah, because you mentioned it earlier, even that our model goes to down to 1.
Yeah, no, it's true. That's good. Let me go, let me see my own thing. We use CrossEntropy, metrics accuracy. MNIST loss. It's gotta, I think it's the architecture. So if we run this one, yeah, that does it. And then we run this one, run that one, and now here, we want to use our own DLS. Let's just say, where does the N out go here? Was it like that? Okay.
It had an underscore after the N, I think.
Let's try it. Nope, doesn't like it.
Even more errors with that.
Yeah.
Oh, four-dimensional.
The error says CNN learner. CNN learner. DLS architecture normalize. And output retrain. If N out is none, N out will be equal to the gets classes from DLS. Assert N out. It's not defined and could be inferred from data. So it should have inferred it. Set DLS.C or pass N out. Model create CNN model architecture N out. Assertion, oh, that's an assertion error. N out is not defined, so it could not infer it and could not be inferred from data. Yeah, so DLS.C. Let's see if we can't print out DL. Well, yeah, it's just the way we did this. Huh? Go ahead.
I was going to say, whoever mentioned that a little bit ago, printing out the shape might be a good idea, because when we gave N out equals 1, it listed the shape was different or something in the printout.
Let me do, I guess I'm going to change this to 2. And I'm going to leave this accuracy, cross entropy, pre-trained ResNet. All right, let's just try that. Seems to have learned. Yeah. It still cannot define. Set DLS.C or pass N out. Yeah. Yeah, so anyway, so I think, the key thing is, the formatting is probably not correct. So I'm just going to switch this back to the DLS. We would have to take a look at our data, convert it into this data, and then that should work. So let's go ahead and run this one. Yeah. All right, and that gives us 99% accuracy. So I'll take a look. I'll take a look to see what the difference is, but I'm guessing it's something that we have in here. So that's it. This concludes the foundations. Okay, we got pretty far. You can see we got as far as, I would say we got as far as this, right? So we basically introduced multi-layer perceptrons. Now you guys can add deep learning, right? So you could add other layers following this approach, add more layers, and that should give you deep learning basically. So are there any questions?
Maybe I have a question here. So I just put a n out equals 1 and I got a same runtime error, kind of what you received. It says expected 4-dimensional input for 4-dimensional weight 64377, but got 2-dimensional input of size 256784 instead.
Can you put that up in the share the
Yeah,
screen?
Sure. You have to let me do it again.
Oh, I have to stop sharing myself.
Oh yeah, that would help. Share screen, share. Okay, pull this over here. So
expected 4-dimensional input. All right, so expected a tensor that is 64 by 3 by 7 by 7. What is that? But got 2-dimensional of size 256 by 784. So that's what we have, right? Batches of 256 by 784. Why does it expect? Oh, no, why? So that looks like we're using a CNN learner, right? Yeah, we're using a CNN learner. ResNet. Oh, leave it.
Oh, sorry. Okay, it was giving a bunch of feedback, so I thought I'd stop sharing.
So what I can tell you is that by looking at that 64 by 3 by 7 by 7, it could be that the batch size of that image data loaders by default is 64, not 256. So that would account for that 64. Do you understand what I mean by that?
I believe so.
Yeah, so that one I think I understand. The 3 by 7 by 7 is probably the images that were 28 by 28 and they've been max pooled, which basically means that they're usually cut in half during the layers. The 3 could be for RGB because this CNN learner actually can work with color images. Do you know what I mean?
Yep.
So that's probably what it is. So so that makes sense. So we would have to tell the CNN learner all of these things. So like I said, it's definitely a formatting issue where the data that we're loading from MNIST already has these dimensions. Scroll up in that, because that's several errors that you got in there, but
oh yeah.
A first whatever. Yeah. Yeah. So anyway, don't worry too much about this, I think.
Okay.
Yeah. Because the idea with this is that it should show us, right? So it should show us, we can use the learner here. And using a CNN learner, we need to basically package the data a little bit more. Okay, we need to package the data a little bit more. We had done the data block thing. So yeah, all right. So anyway, we'll stop here. My suggestion is I'll take a look at this, try to figure out what the issue is to make it consistent with our DLS. But I also leave that as homework for you guys. Just try it out. So try playing with these and then see if you can't modify DLS, our own DLS, to fit in the CNN learner, okay? So just, it's not homework, but just try to do that, okay? So anyway, I'll stop the video now, and then the time that we have left, let's just talk about the homework. All right, so I'm gonna go ahead, I'm gonna save this one. This works. Okay. Let it finish. All right, I'm gonna stop sharing. That, by the way, concludes our discussion of fundamentals. My plan next week is to, just the first half, we're gonna do convolutional neural networks. So I wanna remind you, you should be seeing what? You should be seeing calendar. I want to remind you that today's the 21st. So we finished the topic, and next Monday, the 28th, the first half from 2:30 to 3:50, I'll introduce the topic of CNNs, which kind of builds in from this. And then during the second half, you will have your midterm exam. Okay, and then after that, we'll look at other topics and then spring break. Does that make sense? Questions?
Yep.
All right, so I'm gonna go ahead and stop the recording now.